Cool. So for our second talk, we have Istvan, talking about tackling unconventional registration problems with the Tensor Image Registration Library. Istvan is a medical doctor, a Hungarian-British medical doctor specialising in neuroimage analysis. He earned his PhD in biomedical imaging at the University of Oxford in 2021 and is currently working as a postdoc at the Martinos Center for Biomedical Imaging in Boston. Istvan is best known for his work in microscopy-to-MRI registration. He is the lead developer of the Tensor Image Registration Library, which has been used in several labs all over the world. He received multiple awards for the International Society of Magnetic Resonance and Medicine. Oh, Istvan, take the stage.
Thank you very much for the introduction, and I'm sending a very warm welcome to all of our attendees online and also in Auckland, and potentially from the Martinos as well. I can't tell because I'm signing in from home. So hopefully if I can share the screen, you will see my slides as well. Yeah, I just need to jump back to the first. Okay, so hopefully you can all see the slides and you can hear me well. So my name is Istvan N Huszar. I did most of this work in Oxford, so that's why you can see the Oxford logo on top. And I very recently moved to the Martinos Center where I'm jumping into AI. This talk, just to give you a disclaimer, is not going to involve any AI. So this is all about traditional optimization. And I put up this nice figure from the Big Brain paper on the right-hand side of my title slide. That is to show you what is capable in MRI microscopy in terms of in the field of microscopy to MRI registration. So you might think that this is an MRI volume, but it isn't. It is actually a reconstructed stack of microscopy images, more than 7,000 images that required a sheer more than 1,000 hours to collect on its own, not to mention the data processing power and time. So there are applications when we can't do all of this, but we still want to make some comparisons between microscopy data and MRI. And for those applications, we need to be able to align our data very well. And we found, at least in Oxford, that not many tools can do that very easily and readily out of the box. So that's why we developed a tool, which we call Tensor Image Registration Library, that helps to solve some of these issues. And today in this talk, I'm going to highlight three projects that this tool has been applied in. They all are similar in the same sense that they're all unconventional registration problems. And for the context of this talk, what I mean by conventional registration is any application that concerns the same number of dimensions. So either it's 2D to 3D or 2D to 2D or 3D to 3D registration, or it concerns the same modalities, so MRI to MRI, microscopy to microscopy, but not between those. Excuse me for the background noise here. So what we found is that a tool that makes strong assumptions about the data is usually not flexible enough for these unconventional tasks when you have to register 2D to 3D or MRI to microscopy. That is an example of NERT and FSL. A tool that makes no assumptions about the data is usually too impractical to implement in an unconventional setting, and it requires a dedicated person to work on that. Let's see ITK for that reason. So with TIRL, we aim to hit a compromise between these two extremities. So what is TIRL? It's a microscopy to MRI registration toolbox with customizable pre-baked scripts. Does it use deep learning? No, until you implement your own extension, because it's designed to be modular and customizable, and it's entirely implemented in Python with some libraries in C just to speed up some processing. So take a look at how TIRL is organized. At the core of this library sits the T-image format. It's a universal image container, which allows you to define an image on any kind of domain. Let it be a rectangular grid, a collection of points, or a three-dimensional volume. And at any point of that volume or grid, you can define values which are scalar, vector, matrix, or tensor values. So with this image, you can define transformations of the domain. And the transformations are obviously either linear or nonlinear. And the good thing is that you can chain them up. You can stack as many transformations after each other as you'd like. You can create your custom transformation chains, and you can optimize the transformations either by one or by a collection of them, create different combination of them, merge and split the chains if necessary, and combine them with FSL transformations, because all these transformations are entirely interoperable with FSL. And then for optimization, choose which transformations you want to optimize, choose a cost function, choose an optimization algorithm, and that's what defines your registration script. So what TIRL has is a collection of these registration scripts for which we made these choices, and they are suitable for particular applications, of which I'll be showcasing 3 in this talk. So for unconventional MRI microscopy registration project, the first one that I'm talking about is when we have only single sections of histology, as you can see by the colored little labels here. And those are taken from different parts of the human brain. And then we have the whole volumetric MRI data as a reference. And we want to align the histology data with the MRI. But as you can see, this is not 3D to 3D. This is 2D to 3D registration. And this is also part 2 whole registration. And let me not mention that some of these sections are actually curved in space. So it's not even an affine registration alone. It has to be a deformable type of registration. So there are a lot of complications here, which I'll dive into in this project 1. So for this case, we collected MRI data in a post-mortem setting, and it was multimodal MRI data. And then these brains were transported to the neuropathology unit where it was sectioned, and the dissection process was actually very carefully documented. So as you can see here on the bottom row, the sections of the brain were actually photographed as we cut them coronally, and small blocks were removed from these sections, and the blocks were photographed too. And the slices were photographed after each of the blocks were removed. So we've got a pre and a post image of every single slice. And from those blocks, we sliced 5 to 10 micron thick sections, which then went to histology processing. And that's how we got these little pieces of histology, which then needed to be registered back into the post-mortem 3D MRI volume. So for that, we created a pipeline in TIRL and the previous formalism that I described to you, which is a 3-stage pipeline. So every single stage of this pipeline is a separate registration script, which solves a particular registration problem. So stage 1, you can see we moved from the histology slide to the tissue block. So this is a histology to photograph the registration. Here we were working with different modalities. There are deformations, staining artifacts that need to be taken into account. And these registration script is optimized to do that. In stage 2, we move from the tissue block to the big slice, and that is to insert parts into whole. In stage 3, we tackle the most difficult problem, which is 2D to 3D registration, photograph to MRI. So if we take a closer look at each, to bridge the modality gap, I'm using MIND. This is a modality independent neighborhood descriptor. It is enhancing edges at first sight, but it's a little bit more complex mathematically, and you can look up this reference for what it exactly is. And that allows us to directly compare images of different modalities. So we can actually just subtract the images after we computed these MIND transformations to tell us how similar they are. And we can feed that difference into a Gauss-Newton optimizer to calculate the deformation field, add regularization to make it smooth, and apply the transformation in an iterative fashion. That is to achieve perfect registration with the tissue block. And that accuracy, we measured in a few different samples, we found to be less than 0.4 millimeter based on median contour differences. And that compares very favorably with ants, actually, if you see the other bars on the right. the ends produce much bigger errors on these sections. In stage 2, we employ an automated method of slice matching. So here we take the photographs which are taken during the dissection process. We register them using the TIRL framework. And then non-overlapping areas are highlighted as potential insertion sites, to which we then try to fit in using, again, registration, one of these blocks. And where the fit is the best, that's where we perform an actual full-blown nonlinear registration. That is to achieve slice to block to slice registration. And we found that, again, based on contour differences, this registration was accurate to the figure of 0.2 millimeters. And here comes stage 3. So that's the 2D to 3D registration problem, which consists of 4 different substages in itself. So in order to register the coronal section photograph into MRI, we need to designate a block of space. This rectangular search space is defined to be the scope of the registration. So the slice won't move out of this space. And then we will make rigid and affine adjustments to it until it's perfectly finding its position in MRI space. And in the last 2 steps, we start to very carefully introduce deformations, first in plane. So you can see that only within the plane we're deforming the image first. That is to compensate the histology sampling nonlinearities. And then we introduce out of plane deformations as well, which is to compensate for the bulk deformations of the brain. And once we combine these, just have a look at the results that we can achieve with this pipeline. So on the left, you can see a slice photograph, which is registered into MRI through the 4 different stages. And if you only look at 4, you can see that the contours of the gray and white matter matched up really closely. And that is up to deformations of 6 millimeter out of plane. So this was a freehand cut through the brain, and there can be big deformations, which this tool can compensate for. Using synthetic slices, we were able to measure the accuracy of this slice to volume registration, which is found to be, again, accurate to 0.2 millimeter figure. In fact, this is better than what human observers can do. So initially, we tried to quantify the accuracy of the algorithm by ourselves trying to create landmarks, anatomical landmarks that are matching between these slice photographs and the MRI. So we were scrolling back and forth in MRI space. You try to find anatomically matching positions. And you realize that whenever you do so, you are this far away from the actual positions that the machine was able to find for you. So we were several millimeters off with our best guesses. So that was very convincing. But the fun fact about TIRL is that with all those 3 stages optimized, we can take a transformation chain from all those 3 stages, concatenate them into one, and achieve an end-to-end histology to MRI space registration, which is invertible. So you can go from MRI space to histology space as well. And that allows you to directly compare voxels and pixels from the different modalities. And if you, just like us, have a different variety of modalities on either the histology and the MRI side, then you can actually make multimodal comparisons between various histology modalities and various MRI modalities, comparing vectors of information on both modalities. Okay, as a slight extension to that, I just wanted to mention project 2, where the task was, again, in the same human brain, post-mortem MRI, to register small sections, but without the intermediary photographs that you were seeing in projects 1. So can we do that is the question. So the reason we had to do this is because the only way to sample the motor cortex is by not cutting the brain into coronal sections. Instead, you can see that a block of tissue was actually directly removed from the dorsolateral surface of the brain, and it was actually cut in half, and the histology section came from the middle of that block. So what we have here is the histology section, the MRI volume, and a single intermediary image, which is the block photograph, as you can see here. And you can imagine that with using the previous tools, we can register the histology to the block face image. But there's a problem because we cannot easily match the block face into MRI space because this block can fit into so many places that it's an incredibly vast search space to traverse. So we have to do something clever here. And what we did is that we did cut the brain into sections and we did take a picture of that, but those sections were now damaged. And you can see that these edges were actually created by our previous sampling of the motor cortex. So what you can do here is to take 2 consecutive coronal sections on which you mark these edges, and then you register them using our 2D to 3D tool into MRI space. And that will take these annotations into MRI space. So you can see it on the right in reconstructed MRI space, the little red annotations. Those mark the outline of where the motor cortical block was sampled. And fitting a plane to that gives us an actually good idea where the histology section was sampled from. And we can initialize the histology section into that space and run the regular 2D to 3D optimization algorithm that we created to find the best position. And as you can see on the right, we can achieve a pretty decent registration between the histology and the MRI space here as well. Okay. So I'm trying to spend a little bit more time on project 3 because that's what most people are interested in. And that is about a monkey brain that we sectioned coronally. But instead of taking just small sections, here we slice the whole brain into very densely. And that is very similar to the big brain approach with one little difference that I'm going to explain in the next slide. So here is just a recap that in the Big Mac dataset that I was working with, we had MRI modalities of GRE and several diffusion modalities. We published this very recently in the Nature Communications, so you can look this all up there. And then we take the brain, we slice it coronally, and then we take the slices and create polarized light micrographs and histology sections with different stains. So once we have this data set, the challenge is obviously to reconstruct the volume from these sections of different microscopy information. And ideally, you would not want to take them separately, but you would want to take them all and reconstruct one single volume that has them all in order as they were sampled. So the little caveat that I was mentioning, which makes this different from the Big Brain project, is the way of sampling. So we tried to future-proof our data set, and we designated 7 samples to be taken to constitute a one block, and that had a thickness of 350 microns. So after that 350 microns, another 7 sections would be sampled, but only the first 3 of those 7 sections would be used at the present time, and the rest of the 4 sections would be kept for future use, whatever researchers in the future might be interested in. So these 3 modalities are the NISL, the Gaussian, and the PLI modalities, and they're separated by 50 microns, but they form triplets, and the triplets are separated by much larger distances. So that's what I called pseudo-regular sampling. So you can't just assume that the slice spacing is constant between all these images that you have, but it follows a certain pattern. And with our tool, you can take this into account and do direct microscopy to MRI registration, which means that you don't actually need those intermediary photographs that I was showing you in project 1 and 2. Here we do direct microscopy to MRI registration. Again, we're matching the modality gap between all these histology sections and the MRI by computing the mind transformation. And for this purpose of the Big Mac registration, we introduced a 2-stage pipeline. So in the first stage, we take the slices of microscopy individually, and we register them one by one to MRI, completely independently from each other. And you can probably feel that there's something suboptimal there because you would need to be able to constrain your registration so that slices don't get intersected with each other, right? And that's exactly why it's a 2-stage pipeline. So stage 2 addresses that problem and takes the ensemble of the slices and creates a perfect alignment for all the slices. But stage 1 is essentially the same thing that I introduced in project 1, so the 2D to 3D registration. And stage 2 is what we're going to have a closer look at here. So this is exactly the same. After stage 1, you can see those intersections. This is the kind of result that you would get from slice to volume registration individually. And you want to regularize this stack to make it an actual good fit with the MRI. So this is where stage 2 takes off. It uses the output of stage 1, and it chooses the best 60 slices. It estimates the slice gap, the average slice gap, and the average slice orientation, and it pins it down. And once it pins it down, it then moves on to further fine-tune the rigid parameters of the individual slices, making it a little bit more jagged again. But that in the next iteration, we select all these 60 slices plus the next best 60 slices. And we again estimate the average slice gap and the average orientation. We fix those. And again, we fine-tune the alignment of the slices individually. And we keep repeating this process until we recruit all the slices, at which point we finally fix the slice gap and the orientation, so making all slices parallel and nicely aligned. And that's the moment when we can introduce 3D deformations to the ensemble of the slices. Given that registration result, we can visualize how the microscopy data aligns with MRI by creating interpolated versions of the registered histology data. But all of this is done at high resolution, so you can zoom in as much as you want. You can make MRI voxel to histology pixel comparisons at any scale that you want. All the transformation chains are easily manipulatable. And that is to show that the nonlinear registration at the end just does a better job of aligning things. So there's value in doing that. And so how accurate is this registration, and what can you expect if you don't have a dense sampling of the slices? Well, we found that the accuracy is pretty much on the same level as I was showing you in project 1, that 0.2 millimeter level. So if you have a single slice that you want to register to MRI, this is roughly the accuracy that you can count on. And here's just an example to show you that once we select from the registered data set a single voxel and we reconstruct the average diffusion fiber orientation from that voxel, we do that from the MRI data and we do that from the histology data, and the two things align really, really closely with each other. So that is actually one of the purposes of this data set, to validate MRI diffusion metrics based on what we can see in histology. So I hope with those examples, I've convinced you that TIRL is a unique tool, which is able to do things that other registration tools may not be able to support readily out of the box. And I can assure you that it's more customizable and there are more projects that it's being used in. I just didn't want to talk over the entire afternoon. It's an open source package, it's extendable, and you can download it. In fact, you might even have it already installed on your system because it is deployed with FSL. Just that the FSL version needs an update, and I'm actually currently working on it to release the newest version in FSL. So feel free to get in touch with me if you're interested in this scope of work. This is no longer my main focus, but I'm still actively maintaining this library, and I hope it will live on for a long time. And with all that, I'd like to thank you for your attention and invite you to ask any questions.
Awesome, great talk, Istvan. Any questions, Gonzalo?
Yes, great talk, Istvan. Thank you very much for sharing that. We have a similar project working on the olfactory bulb that we also slice the olfactory bulb, but we don't have a target. But we feel your pain and all this task of trying to register and look anatomical at the end. My question is regarding, you mentioned regularization a few times. I wanted to know what kind of regularization, and also if you have thoughts on adding mechanical constraints of the tissues or something in those directions.
Excellent question. I'm aware of works that try to use elastic transformation models and try to constrain the regularization, try to constrain the transformation based on the elastic modulus of the tissue, what it could be. I think that's a viable approach. I'm not using that here. So in terms of, so there are two different types of regularizations that are going on here. First is the nonlinear deformation that needs to be regularized. That's something that I mentioned in project 1. That is just a simple gradient magnitude type of regularization. So we try to penalize high gradients within the deformation field. So here, when we calculate the deformation field, we take the derivative of that, and we apply a penalty on the magnitude of the derivatives. That's the regularization that I'm using here. It's called diffusion regularization in literature. And in terms of the slices, when we have multiple slices densely sampled from the monkey brain, there's no explicit regularization of the deformations there, apart from the fact that we always use bounded optimization. So when we introduce these deformations, which are deforming the slices out of plane, we always limit them to not exceed a certain number of millimeters, and that's usually 3 millimeters. That's one way of implicitly achieving this regularization. And another way is obviously to, in this step, when you take all the registered slices and then you estimate the average slice gap and the slice orientation, and then you pin that down so that all the slices remain parallel to each other, and then you allow them to jiggle around a little bit to find an even better alignment, but only until you come with another iteration and you fix it down again. So that is providing some kind of more implicit regularization in this dense histology reconstruction approach.
Thank you.
Thanks, Istvan. Hamid here from the ABI. Great talk, thank you. So I've got 3 questions, which I am gonna shoot them away one after another one. The first one is kind of related to the previous question that you answered. That's the biggest challenge that you had in registering deformations, and how did you actually, what was your approach to tackle that?
Yes, so there are limitations of what my deformation model can achieve at this point. So I'm always aiming to constrain my deformations that they are all diffeomorphic. So the Jacobian determinants never fall under 0. That's the most thing I can say. So obviously this was all about a lot of trial and error work and optimizing things which were working visually. One thing that I can say is that, and that's definitely a development work for future. If anyone is interested, if there is an artifact in histology that can be fixed, like a TIRL, that or you look at these histology examples, which is taken from the hemispherical portion of the brain. So if these hemispheres go apart very large distances, then that kind of transformations are not being I'm sorry, let me start over on this. So large deformations are not currently covered in my transformation model. So all this is small deformations. And for these applications, they used to be enough. But for other applications, when the deformations are large, because hemispheres or gyri move apart from each other, you might need to introduce LDDM type of transformation model. Yeah, that's my answer for that.
Thanks. And the second question is with regards to project 3. Have you assessed repeatability of DTI registration in 2 consequent scans? And if so, what was the validation accuracy?
Sorry, what needed to be repeated?
For example, have you done registration of the diffusion data in 2 consequent scans and making sure that the accuracy that you were reporting to, I think it was 0.3 mil, was repeatable in, let's say, 2 consequent scans of DTI, or was it just based on one round of scan?
Okay, yeah, I see that. That's a good point. I mean, with the Big Mac data set, we have a lot of diffusion scans. I wasn't the one who oversaw these, because the first author of this paper is Amy Howe, and she's the primary author of the whole data set. So I would say that in this case we only did one registration, and that was actually not the diffusion scan, but it was to the higher resolution GRE scans. So the higher the resolution of your MRI, the more accurate your registration will be, and for that reason we prefer to register to the GRE modality. That's one thing that I can say. Although we replicated the same results in mouse brain as well, and there are 2 other groups which are doing the macaque. So basically replicating what we did in Big Mac here, and those are ongoing projects. So from their results, I can confirm that whatever we see here is visually repeatable. It's not that we tested the accuracy of those registrations. So pedantically as I did here, but I can certainly see that the general pattern of accuracy is being repeated. And what I did more extensively is a validation in project 1 using synthetic slices, where you take 10 sections of the MRI data, you add noise to it to make it look different from the original data, and then you perturb the position and the orientation of those sections. You even curve them up into 2D parabolas, and you try to register them back into MRI, and that succeeds with the accuracy of 0.2 millimeters. So that is, again, very close to that hallmark. So from these ensemble of information, I would say that it's fairly repeatable.
Fantastic, thanks. And the last and quick one is, are your TIRL algorithms GPU based, or are they CPU based?
This is CPU based at the moment.
Thanks.
I also have a question. So about the registration technique, I see you compared it to ants. I was wondering why you think your method outperforms ants, like the formulation, because I know that ants is also diffeomorphic. Maybe you could also mention what you use to make your approach diffeomorphic.
Yeah, excellent question. I addressed that in my dissertation as well. I don't have a firm conclusion, but I strongly suspect that the difference between the accuracy of TIRL and ants come from the cost function which we used. So as you can see here, I compared a few alternative cost functions and ants. So one is using the Mattis cost function, and the other is using the CC cross correlation. And all of these are ensemble methods. So normalized mutual information in the Mattis and cross correlation are based on ensembles of pixels, and that is just probably subpar versus the mind cost function that I'm using in TIRL. But the mind really focuses on aligning edges in images. So even if you have images of different contrasts where different things are visualized, as long as you have corresponding edges, those will be matched very, very strongly with this cost function. And as you can see on the bottom row, ants is failing. Well, not the bottom row, but in the middle column, ants is mostly failing to align certain edges, which then contributes to a much higher registration error. But in general, on other parts of the images, they may look similar, but some of those faults make it a really bad registration result.
Thank you. Yeah. Cheers. Can we get another round of applause?
Thank you.